Hello, my name is Kevin Carrick with Avnet Electronics Marketing. I'd like to welcome you to this X-Fest 2014 training course. The topic today is building blocks for enhancing user interfaces. Let's get started. If I were to ask you about some of your favorite electronic devices, perhaps a few examples of well-defined user interfaces would come to mind. I'd like to share with you a personal experience that I've had with an electronic device that we're all likely familiar with, the digital camera. This is my own D40 digital single lens reflex camera that my family purchased after my 8-year-old son was born. It's the first camera that my family enjoyed using because it's very responsive and takes a photo at the very moment that the shutter button is pressed. Although I've owned this camera for nearly 8 years now, I've never read the manual for my digital camera. I don't think I ever truly appreciated the ease of use of my camera until this last summer, when I saw my 5-year-old daughter pick up the camera, point in an object of interest, press the shutter button, and look at the display to admire the artistic shot she just created. At that moment, I remembered back to when I was 5 years old, using my father's manual film SLR. I went through a much different engagement experience with that old SLR, which required hours of him coaching me on measuring the environmental lighting, adjusting the aperture, setting the exposure time, and turning the lens body to focus in on the object. My father's camera was far less complex in terms of design than my D40, but required so much more expertise in order to effectively obtain satisfying results. Even today, when I think about my old digital camera and compare it to the camera I used as a child, I feel rather privileged to be using something that still seems so futuristic, as if it were something out of science fiction. So is the point of this course to teach you how to build a digital camera? Well, not really. In fact, I'll be the first here to admit that I don't know a whole lot about what goes into a digital camera design. However, camera companies do know what goes into a digital camera design, and just like a camera company has made an SLR camera easy for me and my family to use, in this course, we're going to consider some building blocks to help you make your own product easy for your customers to use. During this course, we'll try to understand why a good user interface design is so important. We'll explore design considerations and trade-offs in order to get robust and intuitive interfaces into your system. We'll also discover how Zinc 7000 all-programmable SoC capabilities can be leveraged to glue hardware and software design components together within a system. Here's the agenda for today's course. First, we'll take a look at engaging and interacting with the user. Then we'll reach out to the user with some hardware. Then we'll explore some software options for user interfaces, and then we'll take a look at the system level integration using Zinc all-programmable SoC. Then we'll also take a look at an example design leveraging MicroZ system on module. And finally, we'll take a look at where to find more information. In this first section, we'll discuss the importance of user interaction and engagement with your product, and look for ways to improve traditional design mechanisms which have been used in the past to accomplish these goals. Since embedded computing systems are essentially very specialized information systems, let's start with this blank slate and look at the very basic components which must come together in order to produce a working system. The hardware component includes the central processing unit, or CPU, and all its support equipment including input and output devices, storage devices, and communications devices. The software component covers the machine-readable instruction programs that direct the circuitry within the hardware parts of the system to function in ways to produce useful information from system data. The system data is comprised of information and facts that are used by programs to produce more useful information. The system procedures are the policies that govern the operation of a computer system. Procedures are to people what software is to hardware is a common analogy that is used to illustrate the role of procedures within a system. Finally, every system needs people if it is to be useful. The most overlooked element of the system is typically the people element, which is ironically probably the most likely component that influences the success or failure of information systems. The system interface to people is what we refer to as the user interface, and it's a very important aspect of product design because it determines the level of user engagement with your product. Keep in mind that the user interface affects the feelings, the emotions, and the mood of your users. If your user interface is designed poorly and the user feels that they cannot control your product, they literally won't be happy and they'll blame this on your product. In doing so, we strive for mechanisms which enable the system responses to be as immediate as possible in order to help achieve the goal of minimizing operator frustration. We also strive for those inputs to be interpreted by the system accurately in order to maximize operator productivity. The most effective methods for interacting with the user is to engage their senses, and here we're focused mainly on these three senses. The first sense that we want to take a look at is taxioception. This is the touch sense of our users, and we can engage this through some sort of haptic feedback mechanism. The second sense that we want to take a look at here is ophthalmoception. This is the visual sense of our users, and we can engage this through a use of display technology. The third is audioception. This is the hearing of audio from our users, and we can use audio devices in order to engage this sense. In the absence of any of these essential senses, any one of us might find it very difficult to interact with our surrounding. The hardware building blocks we are interested in here help us map our system design to the user's physical senses. In order for the essential human senses to be leveraged in the most meaningful way, senses are often combined to make the realization of the human interface more immersive. Let's take a look at an example of one of the time-honored mechanisms for user input, the electrical mechanical switch, or push button. This building block engages primarily our touch sense and secondarily employs our sight sense in order to guide our finger to the switch using hand-eye coordination. Some systems even employ illumination indicators or auditory feedback mechanisms, which help reassure the user that their input has been detected by the system accurately. For the X-Fest demo in the partner area, we wanted to add these illuminated buttons to our industrial automation demo so that people can more easily identify this as an industrial control system. Seems like a pretty simple task to add a button, right? Well, that's what I thought. Just grab an I/O pin and wire it right up. But wait a minute. If we're creating this demo for an industrial control system, we probably want some sort of way of electrically protecting our system from environmental problems with the button. We approached our supplier partners looking for a solution to this problem, and the folks at Maxim proposed this MaxRefDes12 reference design here, which is codenamed Corona. It is an isolated digital input solution and happens to come in a PMOD compatible format, so it made it easy to connect to our development kit. Also, since it's an isolated input, that means not only is the system protected from ESD from operators, but they are also protected from stray leakage voltage coming from the rest of the industrial control system. Switches have proven to be quite robust over the years. However, there are engineering trade-offs involved with them, such as unit cost. That button which I mentioned on the previous page is somewhere around $10 unit cost. You can also quickly run into lack of flexibility in repurposing buttons, especially if you have a custom panel created for a specific application. Retargeting your system to a different application can involve costly retooling and perhaps rewiring to create a different operator station. Another challenge is the environments in which these switches operate can decrease the reliability of their operation. I did some design work for one company who had built some industrial control equipment, and we had a customer who installed our product in a food processing facility where they shredded cheese. We had one of our units come back from that customer who was reporting intermittent failures, and when we opened the unit to do a root cause analysis, we discovered that a slow buildup of cheese particles had accumulated within our product, and this eventually caused one of the buttons to no longer make proper contact when it was depressed. Some problems like that are difficult to foresee, but once you're aware that they're there, you can take them into account when designing your next product. For the hardware building blocks that we take a look at today, we will want to keep in mind the technological limitations of yesterday's interface components in our search for newer technology which has the potential to make our user interfaces better than those of the past. In this next section, we'll cover some of the hardware that's available today to enable more meaningful engagement between your system and the users interacting with it. Let's revisit our system level diagram for a moment so that we can map out where we're headed in this section. Despite the importance of all these elements in the system level design, we're going to break this design down and focus on how we can use hardware components in our design to help our system more effectively reach the operators who are the people aspect of embedded system design. In this course, we'll take a look at graphical display, touch sense, audio codec, and haptic feedback technologies and see how these fit into our example design. Graphical display technology has been around for quite a while, but it continues to become more miniaturized, and newer technology makes it increasingly easier to design this solution into your end product. There are a wide range of options which are readily available, ranging from segmented and character-based displays to medium-sized TFT display panels to even larger commercial off-the-shelf monitors. There are also factors that you may want to consider for the environment under which a product may operate. Those factors include high brightness and contrast for outdoor viewing operations, or the viewing angle under which a display will be observed by the operator. Even some safety requirements may dictate some aspects of the display, such as protective glass overlays or limits upon the cabling or power used within the display. If you're considering a commercial off-the-shelf HDMI display, there are a few options available for driving video data out of Zynq. Although high-range I/O banks of Series 7 devices are capable of driving HDMI signaling out natively through the TMDS setting on 3.3 volt powered I/O banks, the I/O switching rates top out just above the display resolution of 720p. The first Zynq-based reference designs which used a graphical display needed an HDMI monitor to be connected to them. In fact, if you attended X-Fest 2012 courses, all except one of the Zynq-based demos had an HDMI display connected to them. We have several existing evaluation platforms which implement this piece of hardware from analog devices, including the original Avnet implementation of this chip on the FMC image on board, which allowed it to be evaluated on many platforms which have an available FMC expansion port. For displaying video content out to the HDMI equipment, this has been the go-to chip solution for over 2 years now. It is a very well-known device, and the best part about this device is there are so many reference designs out there which show how to use this chip running bare metal under Linux using ADI's mainline kernel drivers, and even using 3D graphics accelerators through the Logic Bricks IP cores from Xylon. We have several reference design platforms taking advantage of this display controller. One configuration is in our new embedded vision carrier for MicroZ system on module, and another configuration is available in our new Zynq Mini ITX platform. In fact, we have an excellent reference design tutorial up on microz.org which shows how to build up all the software components needed to get this device running under Linux on Zboard or the Zynq Mini ITX platforms. I'll show you a link to that reference design tutorial and some of the related ADI documentation at the end of this course. Because of the challenges in managing all the HDMI monitors and the response we were getting from our FAEs in the field, we knew that there was a need for having an embedded display solution for evaluation kits to replace the large HDMI monitors that were being used to demonstrate Zynq. In searching for an embedded display solution for our evaluation kits, we quickly ran into design challenges in designing our display kits. In doing any graphical display design, we quickly came upon a wide variety of different connectors, cabling options, signaling levels, video standards, as well as basic challenges as how to power panels and their backlight circuitry. We settled upon the Sharp 7-inch LVDS TFT panel because it has a size which fits the lower end, portable range of electronic systems, but it still yields a decent WVGA resolution of 800 by 480 pixels. It has an LED backlight which helped us keep our power requirements down, and we were able to drive the display off a dual PMOD interface on Zboard so that we didn't take up an entire FMC expansion slot. The display we chose has the advantage of consuming a low amount of I/O because of the LVDS signaling, needing only 10 pins on the host processor in order to drive it. Compare that to an equivalent parallel RGB panel which requires at least 29 pins in order to drive the same video data. I'm going to talk about this display in further detail and show how it's a good option for embedded systems. Whether you decide on using a commercial HDMI monitor or an embedded display panel, Avnet Embedded offers a full range of displays and customization options to solve the design challenges involved in selecting the right displays. Avnet has integration facilities across the globe to support the customers in Americas, Europe, and Asia. If that's something you're looking for help with your product development, please let us know and we'll work with your local Avnet FAE to get in touch with the Avnet Embedded division. The next building block technology we'll discuss is something termed TouchSense, where we're targeting the use of an operator's finger or fingers to provide input to the system. This hardware building block is very useful for replacing the electromechanical switches found in many of our legacy designs. Much like the traditional electromechanical button, this building block engages primarily our TouchSense and secondarily employs our SightSense in order to guide our finger to the button using hand-eye coordination. There are a lot of designers out there who are loved with the iPad or the Galaxy tablet, and customers want those touch features in their own product. Unfortunately, a lot of times you have to have above a 10,000 unit annual volume to even start the design discussion, or you have to pay a high NRE. In searching for an embedded touch sense solution for our evaluation kits, another thing that comes up frequently is that many popular projected capacitive solutions require parameter tuning within the firmware when selecting non-standard glass or moving to an enclosure. The touch solution that Avnet chose supports auto-tuning feature, which allows migration to different displays, alternative glass overlays, and also combats system noise. This means that additional tuning is not expected regardless of what system environment you integrate this solution into. If you look at the touch technologies that are out there, there are several that are very popular. Resistive touch sensors are simple and reliable. The primary types of resistive plastic overlays are in 4, 5, or 8-wire versions. They work via a mechanical function of the top layer film being pressed against the bottom layer film, creating a voltage layer divider, which allows the detection of an XY point. Resistive touch sense has been around for a while, and it's the least expensive of the touch technologies. Although these sensors are able to receive inputs from almost any input type, such as a finger, a gloved hand, or a stylus, it's not always the most durable. Surface acoustic wave touch utilizes ultrasonic waves that pass over the touchscreen glass surface. When the glass is touched, a portion of the wave is absorbed. This change registers as a touch event that the controller processes. Surface acoustic wave is capable of understanding nearly any touch object. Today is most popular due to the release of multi-touch products such as smartphones and tablets is the projected capacitive touch technology. Although most typically designed with a glass front surface, a projected capacitive touch sensor can also take advantage of screen protectors, stylized cover glass, as well as vandal or weatherproof glassing. A projected capacitive sensor is manufactured by either single conductive layer forming a grid or etching two separate perpendicular layers of material forming a grid. Voltage to this grid creates a uniform electrostatic field projected outward. A conductive object, usually a finger, breaks that local field at the point it's touching. The controller detects and measures those points along the grid. We also have a path to customization through Avnet Embedded, where there are options for specialized decorative graphics for the touch overlay, specialized glass, and they even have options where dedicated touch sense buttons can be added around the perimeter of the display viewing area. Combining touch panel and display technology is becoming more essential for systems where traditional electromechanical buttons are not practical for use. However, the trade-off here is that you also lose the tactile feedback that comes with electromechanical buttons. If we add another technology into the mix, we can recover that tactile feedback element for the interface to the user. Although haptic technology has been around for a while, it's becoming much more compact and cost-effective, which enables it to be designed into more and more embedded systems. Although there is a range of actuator technologies available, for embedded systems, we typically see 3 of them being mass adopted. The eccentric rotating mass, or ERM, is a DC motor with an offset or non-symmetric mass attached to the shaft. As the shaft and the mass rotate, the surface of the motor it is attached to vibrates along the X and the Y axis. It is also typically the lowest cost option for an actuator, but it usually has the longest response time. Another popular actuator is the linear resonant actuator, or LRA. This is a movable mass with a permanent magnet attached to the spring, with a commutation being driven by a voice coil. As the mass is moved rapidly, vibrational energy is generated along the z-axis. This is typically the best performance per cost option for an actuator today. Another technology that is becoming more popular is piezoelectric actuators, where a ceramic mass converts electrical energy into motion through the piezoelectric effect. Both the ERM and the LRA are considered standard definition actuators, while the piezo technology is considered a high-definition haptic actuator because they have much higher vibrational frequency range. Some of the design challenges we ran into when we were designing haptic feedback into our new display kit is that we wanted an actuator with a balance of these features. The amplitude of vibration needed to be sufficient for the demo setups that we were using, and the actuator needed to be responsive enough to provide feedback for button presses. We also had some mechanical requirements that the actuator be rather compact and simple to mount to our demo kit. We approached our suppliers looking for a solution to this problem, and the folks at Samsung proposed this actuator here, which is a 9mm by 3.4mm LRA. It has a pretty high vibrational force for its size, and it was low power, and it was simple enough for us to mount to the back of our display with some 3M tape. We have a summary of the different actuators available from Samsung at the Avnet URL shown here. So now that we had our actuator picked out, we needed to be able to drive it somehow, so we went back to our supplier partners and asked them to come up with their best solution for haptics drivers. The folks at TI came back with a solution for us with their DRV2605 haptics driver, which was a really good fit for what we had planned for our new display kits. It had an I2C host interface so we could reuse the same communication lines as our touch controller. It was flexible enough to allow customers to evaluate our Samsung LRA or connect up their own ERM if they wanted to. It also helped us speed up our development by leveraging some of the effects waveforms that you get access to with this device. Audio can be another effective technology to use in order to engage the audioception sense of your users. There are some different features offered across a range of codec options to help meet the environmental needs of your product. One option that is increasing in popularity across the electronics industry is Bluetooth. This sort of technology enables users to bring their own Bluetooth-capable audio devices and eliminate some of the complexities associated with designing the analog circuitry around traditional wired audio devices. In fact, we have a PMOD-compatible adapter board for the TI Y-Link 8 module, which enables Bluetooth connectivity to many of our Zynq development platforms. We have a Wireless X-Fest course, which also talks a little bit further about this module, and we have a web page that I'll point out at the end where you can find more information on this solution. We've also been using the ADAU 1761 audio codec from Analog Devices since we released ZBoard, and now it is also integrated into the MicroZ Embedded Vision carrier card as well as our Zynq Mini ITX platform. We now have an excellent reference design that shows how to take advantage of this audio codec under Linux, and this tutorial also includes a hardware platform that is built in the Vivado tools. I'll show a link at the end of this course so that you can take a look into this further if you're interested in learning more. One other consideration you might have for increasing the capability of your system to respond to user interaction is to add positional awareness. There are many solutions available which can enable you to detect whether the user is tilting, shaking, or tapping a piece of equipment. This type of sensor could help you determine which way a product is oriented so that the display can be redisplayed in portrait or landscape mode. You may also want to consider the positional accuracy that your application may need and the number of degrees of freedom needed to achieve the desired positional awareness. For objects in free space, there are 6 degrees of freedom which are usually considered. The first 3 are translational degrees of freedom or offsets from the origin along the X, Y, and Z axes. The second 3 are rotational degrees of freedom or rotations about the X, Y, and Z axes. For our X-Fest demo, we wanted the ability to detect when a display has been tilted past a certain angle. We approached our suppliers looking for a good fit for our new 10-inch industrial display kit, knowing that we needed something with support for industrial temperature range as well. The folks at Freescale proposed the FXLS 8471 accelerometer, which was a good fit for the features we needed since it supports an industrial temperature range and reused the I2C interface that already existed on our display kits. This device is also capable of free fall, motion, and orientation detection so you can design features into your product such as power off on drop detect. The folks at Analog Devices also have the ADXL 362 accelerometer, which comes with Linux driver support. Since this device is available on the PMOD ACL2 using a SPI interface to the host, this can also be a great option for design prototyping. In this next section, we'll cover some of the software options that are available today for building a user interface, and then we'll weigh some of the trade-offs between those different options. In the field, we encounter lots of different software approaches when it comes to creating user interfaces for products. Some of the most common ones we find are shown here. One of the traditional approaches is to write everything yourself completely from scratch or leveraging your own in-house code base. Another common approach is to leverage one of the existing application frameworks that are available for embedded systems such as Qt or GTK+. Finally, web development technologies are gaining a lot of traction as this allows for user interfaces to be accessed remotely and for embedded systems to integrate into existing enterprise data systems. In the bare metal approach, the software design is rather straightforward in that there's no operating system involved, so any access to the memory map is direct with no virtual memory to contend with. This approach also allows for leveraging a lot of existing low-level libraries that Xilinx provides in order to access both hard peripherals in the Zynq processing system or soft peripherals implemented within the Zynq programmable logic. Unfortunately, building up from a very simple design to something more complex can be challenging because there's no underlying operating system framework to add additional software tasks. Since memory access is direct, this approach makes it a lot simpler to debug new custom hardware built within the fabric. We used this approach when we first developed our display controller IP, which is used to drive video data out to LCD displays. Once we got our display controller working in this manner, we added some additional functionality to demonstrate that such a standalone system could also handle touch input from the user as well. This is something that is available to you as an example reference design in our Display Panel Controller standalone tutorial, which can be downloaded from our microz.org community site. Qt is a cross-platform application framework, which makes it an interesting choice for embedded system development. Qt has a Qt Designer tool for designing and building a GUI using Qt widgets. You can compose and customize your windows or dialogues in a what you see is what you get type manner, and test them using different styles and even different resolutions of displays. Since it is a cross-platform environment, while your hardware designers are hard at work developing the hardware platform, the software engineers can work on development of the graphical user interface on a PC until you get your embedded hardware up and running. In fact, I worked on a project once where we implemented this development strategy so we had a first cut of the user interface completely running even before we got our first hardware prototypes in. Since it is such a popular framework, there are a lot of tutorials around Qt development that you can find in YouTube videos, and Xilinx even has a wiki page which covers building the Qt libraries for Zynq. Here's a good time to mention that the Xilinx Zynq-based targeted reference design is an embedded video processing application designed to showcase the features and capabilities of the Zynq all-programmable SoC for the embedded domain. The base TRD consists of two elements: the Zynq 7000 all-programmable processing system and the video processing pipeline implemented within the programmable logic. The all-programmable SoC allows the user to implement a video processing algorithm that performs edge detection on an image using a Sobel filter, either as a software program running on the Zynq all-programmable SoC-based processing system or as a hardware accelerator inside the all-programmable SoC-based programmable logic. The base TRD demonstrates how the user can switch between a software or hardware implementation of the accelerator algorithm and evaluate the cost and benefits of each implementation. An example Linux application with Qt-based GUI is provided with this reference design package. The application provides options for the user using the GUI with the help of a mouse and a keyboard to exercise different modes of the video demonstration. GTK is another cross-platform widget toolkit for creating graphical user interfaces. While it's been under active development for over a decade, it has grown to support a comprehensive collection of core widgets and interfaces for use in an application. Since this approach takes advantage of the windowing libraries from Ubuntu Desktop, it'd be a good solution for an industrial display workstation using a keyboard and a mouse. With this development framework, you aren't limited to just C++ code, since GTK also currently supports over 10 different programming language bindings, so you can have some existing application code in, say, Python. The GTK framework can also support a GUI on top of that application code. The folks at Analog Devices have a lot of very powerful demos which leverage GTK Plus running on Ubuntu Desktop. One example of this is our Zynq SDR2 eval kit for ZBoard, which in and of itself is nothing new, but it's a proven hardware platform that was featured in one of our recent design seminar trainings. The reason that I mentioned the SDR evaluation kit is because here we have this incredibly powerful and configurable RF transceiver. Now, how do you expose all the settings for this device so that designers can get an idea of the effect of a change in settings has upon the performance of the system? Well, this is where the IAO scope application comes in. The ADI IAO oscilloscope is a full-blown desktop Linux application which Analog Devices created to use Linux IAO drivers to access data coming in from the ADC hardware. This application plots captured data in 3 different modes: time domain, frequency domain, and constellation, using GTK Plus as the underlying framework. The idea here is that this GTK Plus application enables developers to visualize the frequency domain to help make important design decisions when they're developing with an ADI device such as the AD9361. When embedded computers were originally developed, those machines started out by having local access only. Now that we have full TCP/IP stacks available on our embedded systems, this enables us to create remote web interfaces using browser-enabled technologies such as AJAX and XML to control those systems remotely. Let's take a look at the flow of an HTTP web service request and subsequent XML response for a servo control application. Here on the right, we have a web browser that requests a specific web service resource from the web server running on an embedded platform on the left by issuing a request message and then waiting for a response from the web server. The request specifies the name of the web service. In this case, it's set position, with an appropriate argument. In this case, we're setting it to 45, which is the degree of rotation. The web server receives the request and interprets what is being requested. Then, the web server handles this request by performing the requested action and returning a response to the web browser. In this example, the web server handles the set position command by assigning the argument to an RC servo controller hardware block and returns the accepted value within an HTTP XML response. The web browser receives that HTTP XML response from the server, interprets the response contents, and displays the updated control contents for the user. In this next section, we'll cover some of the system-level integration needed to enable the user interface technology we've been discussing within an existing design. Here, I want to show you how we took this existing design and modified it to add a user interface into the system. Here's the system block diagram from the Intelligent Industrial Machine as seen in our Making the Internet of Things Smarter X-Fest course. Here in this system, we're using a series of sensor PMODs to provide the system with the data needed to enable a higher level of intelligent decisions to be made by this process control state machine found here in the programmable logic. Each sensor has its own state machine to constantly monitor communications within the sensors in parallel. Data is read from the devices and handed to the master state machine in order to make all the application-specific decisions. There's also a dual port RAM to act as a translation layer between the processing system and the programmable logic so that the processor can harvest some key process metrics for reporting across the cloud. We could add a dedicated processor on top of this programmable logic design in order to handle the additional processing needed for the user interface. But let's take a look at how Zinc can be leveraged to add the user interface within this existing design without adding another processor. So far, we've explored a mix of hardware and software building blocks which can be used to design an engaging user interface. If you worked on these types of system designs a few years ago, you could have a similar system if you could find an application processor which handled all these pieces concurrently, but you're always kind of limited in options. You could also have a bit more flexibility if you added a separate FPGA to serve as a glue logic to the application processor. So, which platform will we use here as an example? Well, today you can leverage Zinc as the single chip foundation for system architecture. Now we can stack our functional blocks into our design and utilize the Zinc programmable logic and flexible I/O as the cement for our system. One key solution that we use to tie these building blocks together in our demo platforms by using a single chip without needing a separate dedicated processor is the Zinc 7000 all-programmable SoC found on our Avnet microZ system on module. Such a diverse set of interfaces requires flexible I/O capability plus an applications processor, and Zinc has Series 7 fabric and I/O to implement custom interfaces to user interface hardware. Also, the ARM Cortex-A9 MP core processor allows for many software subroutines and processes to be run concurrently. In order to accomplish our goal of adding a display into the system, we needed to overcome 3 design challenges in order to move frame buffer data from the processing system out to a display panel utilizing the programmable logic available within Zinc. The first challenge is to move the video frame buffer data from the processing system memory space into programmable logic fabric. The second challenge is to generate the panel timing and serialize the pixel data into a format that the panel will understand. The third challenge is to use I/O to electrically transmit the pixel data out to the panel but minimize the I/O pin count usage. Let's take a closer look at each of these challenges to see how they can be solved by Zinc. A display controller needs to be able to consume a large amount of display data very rapidly, so the first design challenge we faced is how can we move the video data into the programmable logic very quickly and avoid any tearing effects as the processing system writes into the frame buffer. The tear occurs when the frame is read from memory, but that frame is made up of two different write frame sequences. When the read and the write clocks are asynchronous, the read and the write memory pointers will cross each other at some point in time, resulting in a tear effect. To avoid tear, read and write pointers are not allowed to cross each other. The trade-off being here is that if memory is not being written to fast enough, it results in frames being repeated or skipped until the frame write completes. The tearing effect can be mitigated by using the triple frame buffer that is available within the AXI Video DMA controller provided by Xilinx with Vivado Design Suite. By utilizing the high-performance AXI interconnect in Zynq, the VDMA controller can access the frame buffer data that is already in the DDR3 memory space of the processing system. Now that the pixel data has been moved into the programmable logic, the next design challenge is transmitting the data out to the display. Since we're using an LVDS panel to minimize the number of I/O pins required, we need to interleave the pixel data and sync data within a serialized data stream that the panel manufacturer specifies. For this, we look at the display panel datasheet to see how the data is being mapped to the LVDS data channels, and then analyze how this can be realized within the programmable logic. From our experience with display panels in Spartan 6, we knew that having a serialization primitive within the programmable logic would be very useful for streaming out pixel data in the 7 data bit to 1 clock format that the panel requires. Also, it could be ideal to use serialization primitive to generate the 4-3-bit aligned clock that is required by the panel as well. Does anyone watching know the name of a Xilinx FPGA primitive that could help out with that serialization task? If you answered OSERDES E2, you're correct. Here, the video data is supplied by the AXI VDMA IP block on the left, and we use the Avnet display controller IP block shown here to pack the pixel data in order to feed these OSERDES 2 E primitives for serialization off to the right. Here, you can see as a result of the serialization being done in the fabric, the ordering of the pixel data is done prior to the data being passed to the serializer primitives in order to align the bit packing to the referenced pixel clock. Luckily, this RGB pattern encoding format is followed by numerous LVDS panel manufacturers, so when switching to another panel, this aspect of the design is rather straightforward and won't likely need to change. In the ideal situation, a Zynq programmable logic bank gets powered by 2.5 volts at VCC-IO. This enables the use of a differential signal output driver to generate the LVDS 2.5 signaling levels specified by the panel manufacturer. This signaling level is rather straightforward, as you can take the differential outputs of the Zynq device and connect them directly to the panel input pins. But what can you do if you only have a 3.3 volt powered I/O bank available rather than a 2.5 volt power bank? Does anyone watching know why a 3.3 volt powered I/O bank might be problematic for this type of implementation? Well, when we went to add a display panel to Z-board, we ran into this challenge where we had a fixed VCC-IO supply of 3.3 volts for all the PMOD expansion ports connected to bank 13 of the Zynq programmable logic. Since Series 7 high range or HR-IO banks cannot support the LVDS I/O standard when powered from a 3.3 volt supply, this seemed like a dead end for us. However, in looking through the Series 7 documentation, we found that a 3.3 volt powered I/O bank is capable of generating TMDS output, which is similar to LVDS output, but with higher output levels which exceed the allowed ratings for most display panels. Our hardware design group in Hong Kong worked to discover a workaround which turned out to work well for us. On our PMOD interposer board, they added an LDO to the 3.3 volt power rail and used it to power an LDO which outputs 1.5 volts. By adding a 49.9 ohm 1% pull-up on all the differential signals and then connecting the pull-up to the 1.5 volt output of the LDO, we were able to adjust the TMDS signaling levels to within the allowed range for LVDS signaling required by the panel manufacturer. So if you find yourself with the same limitation, keep our display kit in mind as a reference design which can help you solve this problem. Here again, we have the system block diagram for our intelligent industrial control system. What we'll do here is add in our system display design by implementing the solutions for each of those design challenges that we just discussed. This is going to help enable the graphical user interface because now we have the capability to display output and the results to the user by taking advantage of the display panel that has now been added to the system. Thanks to Zinc, we can fit this all into a single design, in a single chip. In this next section, let's take a look at an example user interface design which uses the MicroZ System-on module to help accelerate system development. When Zinc development boards first came out, there was a low-cost display add-on available, the Xilinx FMC HMI module. It has a very low-cost TMA display with a resistive touch overlay. This is a really great way to get a display onto a Zinc development platform, but it does take up an entire FMC slot on the development board. It also turns out that the display panel alone requires 29 I/O pins in order to drive the video data out to the parallel RGB interface. The touch overlay on this display uses the Zinc X80C interface in order to measure the resistive touch, which is great for integration because it saves you an extra integrated circuit chip for the touch controller, but the trade-off is that it costs you at least 4 X80C pins, which you might need for something else. So considering all this, plus what we know about the capabilities of the Zinc Series 7 fabric, we knew that there was an opportunity for a much more tightly integrated touch display solution. When we started looking for an embedded touch display solution for our Zinc development platforms, we set a goal for developing the next one-size-fits-most display solution. We still wanted to minimize host I/O consumption, which meant not only using an LVDS panel to minimize the number of pins consumed, but we also needed to come up with a connection solution which avoided consumption of sole available FMC LPC on Z board. We also wanted to maximize the host board's I/O reuse, which meant avoiding a dedicated display controller and cable for our evaluation boards. We also wanted to integrate capacitive touch sense capability, which is a great fit for embedded systems because you eliminated the need for a keyboard and a mouse. Even if you do not use the exact same display from our display kit, this can still be a great platform for prototyping. Here in this photo, you see a 10.1-inch Kyocera panel on my desk that I was able to bring up using the same adapter board from our 7-inch display kit. All I needed to do was splice the signaling cable from one side to a mating connector which matched the panel and make sure that the proper signals lined up according to the panel datasheet. So far, we've shown how to get display data from the processing system on MicroZ ready for a display panel. Let's show the final connections which are used on our display kit. So far, the LVDS panel data comes out to a display PMOD. Next, we need to move that data out to a display-specific adapter board so that various panels could be connected to the same development board. In our case, we're using a DisplayPort cable since it was the only off-the-shelf cabling solution that could accommodate all of the differential pairs that we needed for a touch display development kit. We can also drop down panel-specific power solutions here for the display logic and LED backlight driver. From that display-specific adapter PCB, we can connect our panel with a panel-specific connector. It seems as though each display manufacturer out there uses a different connector, so this adapter PCB was a necessity for us when we first started down this path. It seems as time goes on, the panel manufacturers are converging on the same types of connectors, but they've not all agreed yet on a standard pinout. So we still need this adapter PCB for the foreseeable future. In order to make the system a little bit more capable, we wanted to provide touch capability for the system. When we went looking for a touch solution, we didn't want to use a resistive touch since that was already a low cost but feature limited solution that was already done on an FMC board. So we chose projected capacitive since it was pretty rugged and had an industrial feature set. When we went looking for a PCAP solution, we found that there are a lot of solutions which exclusively use USB as the host interface. We knew that choosing USB would have really hurt some of the embedded designers out there since that restricts you to a full-blown operating system like Linux or Windows to get the host USB stack. Zinc could have run those full-blown operating systems, but that would have been a design challenge for designers who are using other operating systems on Zinc or a bare metal approach. We ended up finding a Cypress TrueTouch partner and using one of their advanced PCAP solutions, which gives us industrial features like water droplet rejection and thick glove use without needing any fine-tuning in the PCAP controller. This gives us a low-cost I2C host interface, and since we can use one of the Xilinx Axie I2C controllers in the programmable logic fabric, we can get the touch coordinates back into the processing system. Since we're using a simple I2C interface, the driver implementation is much simpler than you would need with a full-blown USB stack running on the Zynq host. Based upon some of the feedback and questions we get from the field, after engineers look at our display kit, it's not immediately obvious to everyone how to leverage this reference design down into your own product. Keep in mind, we designed this display adapter mostly for the benefit of reducing the design impact to our evaluation kits by having to only change one small PCB design should we end up needing to switch to a new display panel. It's been my experience over the years that since displays are a very tough market for manufacturers to be in, displays are subject to remarkably unpredictable product life cycles. Many of you no doubt have already experienced this at least once in your careers, and I'd like to share a personal story to illustrate this. Back when I was a firmware engineer for another company, we were working on a new product development which required a 4.3-inch color display. Since I was part of the hardware bring-up team, I got to sit in on some of the design meetings where hardware engineers developed a seemingly sound strategy to avoid a product redesign by selecting the same LCD panel used in a very popular portable video gaming device. The reasoning was that the video game device would be so popular and be around for at least 5 years that the display would continue to be stocked on the shelves and for us to continue buying for use in our own product. Even though the shipments of the video game device ended in January of 2014 in North America, the display that was chosen ended up going end of life in 2007, causing a PCB redesign and retooling of the plastics in our product. Since we anticipate having to go through this end-of-life experience periodically, we want to help engineers to avoid going through the same dilemma with displays, which is why we decided to promote panels in our display kits which have good product lifetime commitments from our display suppliers. However, just because we select one of these longer life panels doesn't mean you can't still take advantage of this reference design and modify it to suit a different display panel that might better fit your new product. Since we came into this dilemma of wanting to avoid committing to the usage of a single panel, we created an Avnet LCD interface standard which we use internally between our display kits so we can focus on the reuse of a DisplayPort connector and a cable solution. That way, if we decided to change panels, we could reuse the DisplayPort connector across our base boards and simply modify this smaller adapter board to target a new panel. Keep in mind, since we use a DisplayPort connector and a cable, it's only for the electrical connectivity. In no way does our display kit support the DisplayPort VESA standard. As a result of this strategy, there are some areas of this adapter board which wouldn't be useful in your own design, such as this barrel jack or even the DisplayPort connector itself. However, these other circuit areas here, you can leverage reference design reuse from our display kit to help accelerate the design of a display into your own PCB design. Also, these areas here, such as the microZ system on module and the display panel or touch overlay, are pieces you can buy directly from Avnet and design directly into your products. In these next few slides, I'm going to show you a few other key circuit areas which you might find valuable for your own board design. Let's start with the display adapter board shown here. Since most modern displays use an LED backlight with 3 to 6 LED strings, we went out to our supplier partners to look for a solution that can be applied broadly to the panels that we wanted to use on our reference designs. The folks at TI came back with this LED driver, which gives us better than 3% accuracy on the current supply across up to 6 LED strings. On our display kits, we only needed 3 channels of 8 LEDs each connected in order to support the backlight on our panel. So this is one circuit which you can leverage from our adapter PCB and copy directly down to your own board design. Even the footprints for these TE connectors used on this PCB design can be reused, since you can get access to our design files through your local Avnet or Silica FAE. This panel connector down here at the bottom is a very popular panel interconnect which we found was being used on at least 3 of the different panel manufacturers on our embedded line card. So if you're looking for a different LVDS panel, you could still use our adapter PCB to quickly prototype up your system by creating a custom cable to connect up this connector and wire appropriately to your panel of choice. That TE panel connector that we used comes from the TE LCD line of interconnects, and it is compatible and mateable with the IPEX series of connectors that are found on many of the LVDS panels available today. There's even a microcoax option for this cable that supports twin coax of gauge 40 or smaller if that's something that you need for your application. Here's more information on our display kit. We have our Z 7-inch touch display kit available from our website, and you can find more information on that at the URL shown here. We also provide all the source code for the display controller IP as well as the schematics and bill of materials for all of our Avnet created PCB designs, so you're free to leverage as much or as little of the reference design as you need. If you're working with your local Avnet or Silica FAE, you can even get access to the original design files for our boards if you need them. The display and touch overlay used in this design was designed for enhanced display ruggedness in outdoor environments, and it has better long-term touch endurance and performance. It's good for medical and industrial product designs that are operating in a high humidity environment. It can support up to 6 mm thick glass, and it also allows for gloved operation as well. Our display kit was designed as an alternative to existing resistive touch display solutions that are out there. It also connects directly to microZ carriers via the PMOD expansion ports. It also enables display options without the use of the sole available FMC slot. So that gives you some insight in how we're working hard towards accelerating your success by providing these reference designs as a way to reduce your time to market. In fact, I used this display kit when we were prototyping our 10-inch display kit used on our demo. I took this adapter board here from the Sharp 7-inch display kit and did an analysis to see that the power solutions would still support the 10-inch Kyocera panel. Then I chopped the 30-pin LVDS cable in half and spliced it to a pigtail that fits the 40-pin connector on the Kyocera. After the display controller timing was adjusted in the display controller programmable logic IP, I had the new 10-inch panel working the next day. Going through the prototyping experience gave me the confidence to go ahead and have a design group create the new adapter PCB to support the new 10-inch display kit in time for X-Fest 2014. In this next section, I'll show you some of the links that I've mentioned throughout the course, and then we'll wrap things up with an overview of the other courses that are also available in the X-Fest 2014 Internet of Things track. Here's some links to some training and reference design tutorials that may be useful for your development. We have an Introduction to 7-inch Z Touch Display Kit video available up on YouTube at the link shown here. We also have an Enabling Haptics in Industrial Applications on-ramp technical session that may also be of interest if you're looking to build haptics into your next device. The display panel controller standalone and Ubuntu tutorials for microZ and Z-board that I've described in this course are available on our microZ.org website at the URL shown here. You can find more information on the Y-Link 8 PMOD compatible adapter and module that is mentioned in this course, as well as the Zinc connectivity course at the links shown here at the bottom. Analog Devices also has a bunch of information on the Linux device drivers, not only for their ADV7511 HDMI controller, but also for their ADAU 1761 audio device. There's also a reference design that's available for the ADXL 362 accelerometer PMOD that was shown earlier in this course. We've also taken some of the information that's shown up on the Analog Devices wiki and compiled a tutorial that's available on our microZ.org website that shows how to get the ADV7511 and the ADAU 1761 running under Ubuntu desktop on the Z-board platform as well as the Mini ITX platform. Be sure to visit the other courses in the X-Fest 2014 Internet of Things track. Our Making the IoT Smarter course will introduce you to some of the concepts behind the Internet of Things, or IoT, and cover how smarter devices in the IoT can help reduce failures with efficient preventative maintenance, increase productivity by making more complex decisions for themselves, and streamline data that gets passed into the cloud. We also have our Adding Wireless Connectivity to Zinc Systems course, which covers the connectivity portion of the IoT by showing some of the wireless options that are available for Zinc. Finally, in the Adding Smarter Vision to Your Product with Zinc course, you can learn about why Zinc is an excellent fit for machine vision applications. This course will cover some of the design guides for creating a vision system, which is the ultimate sensor. You can also learn about Avnet's new embedded vision kit, which was designed using these same principles. That completes our course. We appreciate you taking the time to learn about building blocks for enhancing user interfaces. We hope you found this course useful and that you learned a few new tricks to help you get to market faster. If you have any comments, questions, or feedback, we'd love to hear about it. and you can pass along any feedback or questions through our course forums at xfest2014.com, our general Zinc forums at zboard.org, microz.org, or picoz.org, or contact your local Avnet or Silica FAE. Combined with our reference designs and technical tutorials, we provide many avenues for accelerating your success. Thank you.